Let's learn about AWS Load Balancers, API Gateway, CloudFront, Global Accelerator, and Route 53. Our goal here is to understand what each of these services do and how do they interact with other AWS services. To begin with, let's take a quick look at AWS Global Infrastructure. The AWS Global Infrastructure consists of regions, availability zones, regional edge caches, edge locations, and high-speed links connecting all of them. All of this is spread across the world. When an end user's request needs to travel to an application endpoint in a region, it normally first travels via public internet until it reaches the AWS region. However, there are ways to speed up the process. We will learn more about this soon. AWS services use this infrastructure. Amongst these services, Load Balancer and API Gateway are regional services, while CloudFront, Global Accelerator, and Route 53 are global services. So let's look at each of these services one by one, starting with Load Balancer. In its simplest terms, a load balancer is a service which can direct a request to one or more targets. This allows in spreading the load across target services. AWS provides elastic load balancers for this purpose. There are several kinds of these. Let's look at them. There are four kinds of elastic load balancers: application, network, classic, and gateway load balancer. Let's start with application load balancer. In simple terms, what can an application load balancer do? It can forward HTTP, HTTPS traffic to downstream systems based on rules. Therefore, it spreads load across downstream systems. It can serve as a single point of access to your application. It can perform health check of instances and handle failures gracefully. It can serve as an SSL termination point and supports sticky sessions. Here are some additional concepts that you need to understand. Listener is a process that checks for connection requests using configured protocol and port. You can define multiple listeners. For example, one for HTTP port 80 and another for HTTPS port 443. Listener rule decides where or which target group the request must be sent. Rule condition can be based on path, HTTP header, query string, source IP, etc. A target group is simply a collection of endpoints or servers which the load balancer can route traffic to. Routing algorithms are configured at target group level. It determines how the load balancer selects target from the target group when routing requests. Default is round robin. Alternatively, you can specify least outstanding requests from routing algorithm. Stickiness too can be configured at target group level. It allows the load balancer to bind a user's session to a specific target within a target group. You can also configure an application load balancer to securely authenticate users, for example, via Amazon Cognito or social identity providers. Application load balancers use X-forwarded HTTP headers for sending client-related information to downstream systems. X-forwarded for header is used for client's IP address. Note that target servers see only the load balancer's IP address by default. To find the original client's IP address, they must refer to the X forwarded for HTTP header. Similarly, X forwarded proto and X forwarded port contain the protocol and port respectively that client uses to connect to the load balancer. Here we have two target groups of microservices, orders and inventory, and the application load balancer is configured to route requests based on path in URL. All /order path requests go to the orders target group, while the /inventory path requests go to the inventory target group. Ideally, the target groups should be spread across availability zones for high availability. So let's look at that. In this diagram, we can see two target groups, blue and green. Each target group spans the availability zones. This clearly provides for higher availability of target services. The load balancer can send requests to these target groups based on routing rules. You can also perform blue-green deployments with such a setup, whereby you release a newer version of a service in only one target group, say the green target group, to test its impact on a smaller set of users by assigning appropriate weights to target groups. For example, you can attach 80% weight to the blue target group and 20% weight to the green target group. Thus, the blue target group gets 80% of user requests, while the green target group gets 20%, allowing you to check for feature impact and stability of your newer releases on a smaller set of users before rolling it out to everyone. Let's look at Network Load Balancer now. Network load balancers work with TCP/UDP traffic. They can handle millions of requests per second at extremely low latency. It supports TLS termination at load balancer or target. You can enable stickiness on target group. So network load balancers are useful for high performance workloads with TCP/UDP traffic. Here's an example of network load balancer in use. We are live streaming media over RTMPS or Secure RTMP protocol to AWS Elemental Media Live Service. However, the Media Live Service does not support secure version of RTMP protocol, so we have a network load balancer sitting before it that serves as a TLS termination point. It receives RTMPS traffic and forwards RTMP traffic to AWS Elemental Media Live. Network load balancer can sit in front of an application load balancer too. Since application load balancers do not provide static IP while network load balancers do, this setup can be used where you need a static IP as entry point to your application. Here's an example of handling multi-protocol traffic using network and application load balancers. The network load balancer here has two listeners, TCP on port 80 and UDP on port 53. The TCP listener is configured to forward traffic to an application load balancer target group, while the UDP listener is configured to forward UDP traffic to another target group which has instances that will accept UDP traffic. This configuration works well for applications that use multi-protocol connections, such as media services using HTTP for signaling and RTP for streaming content. Next, we have Classic Load Balancer. It is used for older EC2 Classic workloads and not used for newer workloads. Therefore, we will skip this. Let's discuss Gateway Load Balancers now. Gateway load balancers act as a gateway and a load balancer. It forwards traffic to and load balances virtual appliances. Virtual appliances are things like firewalls, intrusion detection, packet inspection systems. It listens for IP packets and forwards traffic based on rules. It can maintain stickiness and perform health checks on targets. Therefore, it is a transparent network gateway that allows scaling of virtual appliances on demand. In this diagram, you can see how traffic is flowing into the virtual appliances before it is sent to its destination. Now that we understand these load balancers, let's do a quick recap. Here's a comparison between load balancers with respect to OSI layer, protocol listeners, target types, static IP support, SSL termination, source IP preservation, user authentication, long-lived TCP connections, and typical use cases. You may pause this video here if you want to take an in-depth look. Now that we have covered AWS load balancers, it's time to look at API gateway. Broadly speaking, there are three kinds of APIs you can create: REST APIs, HTTP APIs, and WebSockets APIs. REST APIs provide you complete control over request response and are feature rich. HTTP APIs are low latency, cost effective APIs, while WebSocket APIs are used for persistent connections for real time use cases. What are APIs? APIs are interfaces to your application logic. API Gateway allows you to create, manage, and securely access your APIs. It provides a single point of entry to access backend services, supports authorizers via Lambda functions and Cognito pools, provides rate limiting via usage plans. Clients can be identified using API keys. It provides support for stateless secure HTTP REST APIs and stateful WebSocket APIs. In addition, logging and monitoring of API usage and API changes with CloudTrail logs and CloudWatch alarms. Here's a simple example where API Gateway is routing REST calls to services at the backend. API Gateway integrates with a large number of AWS services. Here are some things you can define on an API Gateway. Authorizer. It controls access to your API. Stage. It refers to a deployment like prod or dev. APIs are deployed to a stage. You can define as many stages as you want and configure caching, request throttling, logging, etc. on it. With caching, you can cache responses from your endpoint for a period of time. API keys are alphanumeric strings given to application developer customers to grant access to your APIs. They also help you distinguish one client from another. With usage plans, you define API rate, burst, and quota limits. It is associated with API keys and stages. On the surface, load balancer and API gateway may look similar, but in spite of similarities, the primary purpose of each of these services is different, not to mention complexity and pricing. Let's do a comparison. Load balancer accepts HTTP, HTTPS traffic, while API gateway accepts HTTPS traffic. No rate limiting or bursting capability in load balancers, while API gateway can implement rate limiting and bursting. No request validation, request response mapping in load balancers, while API gateway supports request validation and request response mapping. No support for cached response versus support for cached response. Integration with EC2, Lambda, and IP addresses versus integration with a large number of AWS services. Health check support versus no health check. Pay for idle capacity versus pay per use. A large timeout versus a relatively smaller timeout limit. Let's discuss CloudFront now. If your application is hosted in, say, a US East region and your users are spread around the world, then it may take a lot of network hops and delay to deliver content to users around the world. What if content could be cached and delivered from a location closer to the end user? This is what CloudFront CDN does. As we have seen before, AWS Global Infrastructure has edge locations around the world. CloudFront uses these edge locations to cache and deliver content to users in geographic proximity, thus improving the end user's application usage experience. Therefore, edge locations are key to serving content quickly to the end user. Here is a simple diagram where you can see CloudFront serving static and dynamic content. The content can be configured to be cached by CloudFront. For example, we would want the static content to be cached but not the dynamic content. S3 bucket and application load balancer here are called origins. CloudFront supports a wide variety of origins. Note that your application domain name points to CloudFront distribution. You can do this in your DNS service like Route 53. Let's go over some important features of CloudFront. CloudFront is a CDN or Content Delivery Network service. It can deliver static and dynamic content. It delivers HTML files, images, videos, APIs to customers globally. Content is served from geographically distributed edge locations around the world. It supports secure content delivery. DDoS protection is provided with AWS Shield, and it integrates with AWS Web Application Firewall for application layer protection. Lambda at Edge feature allows you to run application logic closer to your customer. It supports origins like S3 buckets, Lambda functions, EC2 application load balancer, media store container, media packet channel. Let's take a quick look at Lambda at Edge feature in CloudFront. Essentially, it is executing a Lambda function at a CloudFront edge location. It provides for intelligent processing of HTTP requests closer to the end user. So a Lambda at Edge function can be triggered on following events: viewer request, origin response, and viewer response. So where would you use this? Here are some sample use cases. Adding HTTP security headers on all origin responses. Dynamically routing requests to different origins based on different viewer characteristics. Blocking unwanted bots at the edge, and so on. Let's discuss Global Accelerator now. When a user accesses an AWS application, it goes over public internet until it reaches the destination regional endpoint. This can be slow depending on network hops, available bandwidth, and so on. However, if a end user's request can travel through fast AWS global network, it can reach the application endpoint in AWS much faster, thereby delivering better performance. AWS Global Accelerator allows you to do exactly that. Therefore, it is a service to improve availability and performance of internet applications. Global Accelerator optimizes path from user to applications via AWS Global Network. It does this by moving traffic from public internet to fast AWS Global Network. Application endpoints could be load balancers, EC2 instances, etc. Global Accelerator's static IP allows for easy movement of applications across regions or availability zones without updating DNS. It monitors health of application endpoints and redirects traffic to healthy endpoints in less than 30 seconds. Speed improvement with Global Accelerator can be measured with this tool available at speedtest.globalaccelerator.aws. Here you see how Global Accelerator is configured and functions. You define listeners with port and protocol and routing policy for it, which could be the standard geo-proximity routing or custom. You can define multiple listeners. The targets here are called endpoint groups, which are defined against regions. Every endpoint group can have multiple endpoints. Endpoints could be things like application load balancers, network load balancers, EC2 instances, elastic IP address. To further control and manage traffic, you can define traffic dial for endpoint groups. This is defined independent of listener traffic and is defined at endpoint group level. So, if set to 50%, the endpoint group would receive 50% of the traffic that would have been normally routed to it based on routing setup. Rest would flow to other endpoint groups. When traffic dial is set to 0%, that endpoint group would receive no traffic. This is useful if you want to perform maintenance activity at that endpoint group. Similarly, weights can be set for endpoints within the endpoint group. A weight simply refers to proportion of total traffic to route to an endpoint within an endpoint group. A weight of 0 would indicate that the endpoint should receive no traffic. Global Accelerator comes with static IP, so your DNS service can have a domain name point to it. This allows you to reroute traffic via the accelerator without making any changes to the DNS configuration. So in this example with geo proximity routing, a user in North America will be routed to North Virginia and a user in Malaysia will be routed to Singapore region. If a regional endpoint becomes unhealthy, client request can be routed to an alternate region. CloudFront and Global Accelerator services may look similar, but the primary purpose of each of these services is different, not to mention the complexity and pricing. Let's do a comparison. CloudFront uses edge locations to cache content, while Global Accelerator uses edge locations to find an optimal pathway to the nearest regional endpoint. CloudFront uses multiple sets of dynamically changing IP addresses, while Global Accelerator provides you a set of static IP addresses as an entry point to your applications. Designed to handle HTTP protocol versus best suited for both HTTP and non-HTTP protocols such as TCP and UDP. Pricing is mainly based on data transfer out and HTTP requests versus charges are based on fixed hourly fee and data transfer rates. Let's discuss Route 53 now. First, let us see how a basic DNS service works. When you type a domain name like xyzdomain.com on your browser, the request goes to a DNS service which looks up its records to find corresponding IP address for the domain name and returns that. So now your HTTP request can go to that IP address. Route 53 is a DNS service from AWS. You can use it to map domain names to load balancers, EC2 instances, S3 buckets, CloudFront distributions, API gateway, etc. It can also be used with non-AWS resources. In addition, you can set up routing policies like geo-proximity routing, whereby requests are routed to an application endpoint geographically closest to the end user. There is support for health checks as well. If an application endpoint is no longer healthy, traffic can be directed to another healthy application endpoint. So Route 53 serves as a basic DNS service and it provides additional functionality. When you configure Route 53, the first thing you do is to create a hosted zone. A hosted zone is a collection of records belonging to a single parent domain name. Records contain information about how you want to route traffic for a domain and its subdomains. Hosted zones can be public or private. A public hosted zone contains records that specify how you want to route traffic on internet. A private hosted zone, on the other hand, contains records that specify how you want to route traffic in Amazon VPCs. A private hosted zone is associated with VPCs. An example use case would be an application server querying the DNS for a domain like db.mydomain to get IP address of a database server it needs to connect to. Here's a simple Route 53 setup where domain name is pointing to application endpoints in two different regions. A variety of cross-region routing policies are supported. Here's another setup with two regions. Within each region, an application load balancer load balances across availability zones, and Route 53 is configured to send traffic across regions based on routing policy. Both regions can be treated as active-active, in which case Route 53 can send user requests to a region that is closer to the user using geo-proximity routing policy. Or you can treat regions as active-passive and use a failover routing policy, in which case all requests are routed to the active region. However, if the active region becomes unhealthy, then all the requests can be routed to the standby passive region. With this, we come to the end of our discussion. This should give you a good idea of these services individually and how they interact with other AWS services.